And now the entire summary of this whole deep generative stuff that we have done, right? So here's the summary. So we had these 4 algorithms that we were interested in. So we had RBMs, variational autoencoders, autoregressive models, in which we did NAID and MAID. We'll not talk about pixel RNNs, and GANs, okay? So these are the 4 things that we did. And there were several things that we kept asking about. This model, can it do abstraction, can it do generation, and so on. So abstraction, how many of these models were able to do? Except for, in GANs, do you have any abstraction? No. In fact, you start from some normal random distribution and come to the image. So there is, given an image, there is no Z, right? You don't have Z given X in a GAN, okay? So it cannot do abstraction, whereas RBMs and VAs can do that. What about generation? All of them can do it? Okay. What about P of X? If I want to compute P of X, the options that you have is tractable, intractable, not applicable. If I want to compute P of X, in the case of RBMs, tractable, intractable, not applicable. Intractable, right? Because to compute P of X, you have to sum out the H's, right? Remember that? So it's intractable. For variational autoencoders, so remember, always you had this bad expectation and then you approximated it by something. In the case of RBMs, you approximated it by sampling. In the case of variational autoencoders, by using variational inference, right? So you did not optimize the actual objective, you optimized the lower bound. So there is a difference. That means it was intractable. What about autoregressive models? Tractable, but slow. What about GANs? Not applicable. GANs don't even compute a P of X. What about generating samples or sampling from this distribution? In the case of RBMs, how will you do it? How will you generate samples once you have learned the distribution? You will do Gibbs sampling. For variational autoencoders, you can just pass a Z. I mean, for variational autoencoders, it was simple, right? You take a Z and you just generate the image from there, right? The decoder will do it. For AR models, you can do it, but it's very slow because you do it 1 pixel at a time from left to right. And for GANs, it's very fast because you just pass it through your convolutional neural network or the transpose convolutional neural network and you'll get it, okay? What about the type of the graphical model? The options are directed, undirected. Undirected, directed, directed, directed. You take a Z and then give a X, right? So it's also directed, okay. What about the loss function? Okay, this, since we have not done the math part, so it's KL divergence for the first 3 and something known as Jensen-Shannon divergence for the last one, which is again a sum of 2 KL divergences, okay. So why is it KL divergence? We were always looking at cross entropy, right? Then why am I writing KL divergence? Because the KL divergence is the same as cross entropy if you are trying to, remember that? We have proved this earlier. Because one term depends only on the true distribution and the other term depends on the true and the predicted distribution. So the first term does not matter and the second term is the same as the cross entropy. Everyone remembers that? You have derived this at some point. If not, you can go back and check it. What were the assumptions made by these different models? For RBMs, X's are independent given the Z. For VAs, no, VAs we did make an assumption. It was implicit sitting somewhere in the corner. We assumed that the covariance matrix was, that means the X's are independent given the Z. For autoregressive models, we did not make any assumptions. For GANs, not applicable because we don't really find P of X, right? Okay, and okay, this last part is, so the generated sample, so what's the current state of the art? So you have these 4 different ways of generating images now, right? And doing all these applications which I said, given an image, generate another image and so on. So what's the state of the art right now? So RBMs are pretty bad at it. VAs are okay, the images are a bit blurry, they're not very sharp. AR models are good and GANs are considerably the best among these 4 options, right? That's why you hear a lot about GANs, okay? So this is one way of analyzing all these models and like finding the relative differences from each other. The other is we could actually, and okay, so before I move on, so there's a lot of newer works which look at a combination of these things. So you take the autoencoder idea, you take the adversarial idea from GANs and try to come up with an adversarial variational autoencoder, right? Or you take the pixel RNN idea, you take the variational autoencoder idea and try to come up with a pixel variational autoencoders, right? So these are a lot of combinations of these things are now happening. Why? Because all of them have their own relative advantages and disadvantages. So if you combine them, hopefully the disadvantages should disappear and the advantages should multiply, right? So that's the hope. Okay, so there's a lot of recent work happening around that. And finally, if you look at the overall taxonomy of these approaches, so remember this maximum likelihood. This is nothing but the recipe which I told you, right? Whenever you want to learn a joint distribution, what do? You have a P of X and you want to maximize log of P of X. So all the models that we do have the same recipe. They want to maximize some log of P of X, right? But some models have an explicit representation for P of X. Some have an implicit representation for P of X. So the explicit representation ones are GANs. That's the most important one. Sorry, implicit representation. It does not compute P of X. It just gives you samples from the distribution. So that's GANs. For the explicit ones, you have two parts. One is tractable models and the other is intractable models. So the tractable models are NAID, MAID and pixel RNN because you can actually compute P of X as the default factorization, okay? And the intractable ones are the ones which use this approximate density are variational autoencoders and Boltzmann machines or restricted Boltzmann machines, right? So this is the overall taxonomy of all the algorithms that we have seen, and these three, right, GANs, pixel RNN and variational autoencoders are the most popular ones that you will see nowadays, okay? So with that, I officially end the course, and so I hope you enjoyed it. I really enjoyed teaching it. I hope you also enjoyed learning from it and picked up a few things along the way. Now I would like to do an important thing. I would like to call all my TAs on stage and really thank them for all their support and effort throughout the course. And they've done a very, very fantastic job. It's not very easy to make these slides. And I can really be a pain in the neck when it comes to these things. Replace neck by any other word that you want. And so it's very, very hard because I make these storyboards and I'm very particular about that this image has to come at this pixel location and not anywhere else and so on. And the equations have to be in a certain point and so on. So they've lived up to all that and survived through it. So they really deserve a big hand of applause. So please join me in doing that.